So first thing we should, because there's no external forces, we assume that the momentum is conserved, right? So we can say P1 equals P2. Now the difference here is that because it's inelastic, we're going to have a mass total times a combined velocity post-collision. There's no A and B on the right side. Are you with me? On the left side, we're going to have P1 or A1 and then PB1. But the right side, it's one entity. The bullet is in the block. So we're not going to have separate velocities. We're going to have a single velocity post-collision. And it's going to be the mass of the bullet plus the mass of the block times their velocity, whatever their velocity is post-collision. Are you with me? So we're going to have the mass of the bullet, the velocity of the bullet before the collision, and then the mass of the block and the velocity of the block pre-collision. Night for Rito. So this is what I was saying. All right. So back to the problem. The momentum before equals the momentum after. The momentum of B is 0, the block. Before equals the momentum after because the horizontal momentum is conserved right at the collision. But after the collision, the friction starts to act on it, and the tensions on these wires also act on it, so can't really say that the momentum is conserved post-collision. Okay? So post-collision, we're going to need some other method to figure out what this V2 is. Okay? How do I figure out what you are? Any ideas? Maybe one of the techniques you might have just learned? We know that the kinetic energy plus the momentum, or the potential energy, sorry, before equals the kinetic energy plus potential energy after. Okay, so if we're looking at the reference frame of this up here, before being up here, we were at the bottom, we were moving that way, and we had a kinetic energy of what? 1/2 the mass total, the velocity, and then no potential energy at the bottom. And then once we get to the very top of this motion, we're going to have the all potential energy, which is mass times gravity times height. Okay, with the potential conservation of energy, always one of them will usually go. Oops, wrong one. One of them will go to 0 on each side to begin with, right? So it was purely kinetic energy right when the bullet collides, right? And then once it moves to the very top of this thing, it's going to pause for a split second before it swings back down, right? So it's all energy at the very top. Do you understand that?
Yeah.
Okay. So what are we looking for out of this? We want to know what that velocity is. That's our V2 that we're looking for.
Okay.
So do you see why this is a good problem for a test? Not only are you forced to use conservation of momentum, but you also have to use conservation of energy. So we got 1/2 the total mass, which is the 5 kilograms or 5 grams. So 5 times 10 to the what to make it into kilograms. Good. So you could go like this if you want to do conversion. And kilograms is larger unit, so we put 1,000. And if you put a 1 on the larger unit, you'll never have to use decimals or negative exponents. And then because it's in the bottom, it'll be -3. And plus the block, which is 5 kilograms. And then the velocity we're looking for, the mass total again is this. So you can see actually the masses are going to cancel. I don't even right? Do you see that?
Yeah.
This is the mass total as well. And then that'll be equal to GH. So we've got V2 is equal to 2GH. What am I forgetting in kinetic energy? What did you not catch?
It's 1/2 times mass and velocity squared.
Yeah, I forgot the squared, right? So that's going to be 2GH here. So V2, that's going to go into the other formula, is going to be the square root of 2 times the gravity times the 3 centimeters that we came up with. And make sure you convert that into meters, which is 0.03 meters. You see how I did that?
Yeah.
All right, so if you were to do all that in your calculator, you're going to get 307 meters per second. That's going to be your V2. And then the mass of the bullet, we're almost there. I mean, the velocity of the bullet, we're just going to have to plug and chug. Okay, ooh, running out of space. So here, I know the mass of the bullet is 5e, let me use yellow, a little brighter, 7 meters per second, which is a little bit more reasonable, right? That block flying up in the air like that at 300 miles an hour, I should have thought to myself, wait, that's not right. This guy is the one that's 307 meters per second. Okay? So let's recap real quick and then do whatever you want. So the bullet collides. At that instant of collision, its momentum is conserved, the bullet block system. But the moment it starts moving, the external forces of friction between the bullet and the block and the tension between the roof and the rope and the block no longer conserve the momentum, so we had to use conservation of energy to calculate what this velocity was. We knew that this went to 0 because it was at rest, and then it was just kind of fell into place. Do you have any questions about that?
No.
Okay, you want to take a snapshot?
Yes.